Hello again. This is section 2.7 of James Stewart's Calculus Early Transcendentals book, and it deals with the derivative and rates of change. Chapter 2 deals with limits of a function, and here we go with one of the most important concepts in calculus, the tangent line. All right, so earlier in the chapter, we discussed average rates of change, and we dealt with finding slopes of a secant line connecting a point A f of A to a random x f of x. So if we look here, if we want to take a look at A, and we go out a distance x, and we go up to the graph, we know that this point on our curve is x f of x, and we know that at the point A, our point on the curve is a f of a. And if we were to connect the dots between a f of a and x f of x, and we took the slope of the secant line, that would be y2 minus y1 over x2 minus x1, or the change in y over the change in x, and we would say that this is f of x minus f of a over x minus a. No limits whatsoever. But now, if we are looking at trying to find the slope of the tangent line, because we know that we can find the equation of a tangent line if we're just given the slope of the line and a point. So if we're interested in finding at point A, at this point, the tangent line, and this would be our tangent line, the one in pink, how would we do it with only one point? How would we find a slope? In general, if we want to use the slope definition, we need 2 points. So that's why we're looking at developing a formal definition for the slope of the tangent line at a point A. And we do it by letting, if we have this x, and this would be our point x, and we would be taking secant lines there. That's not really the slope of our tangent line. If we get a little closer and we take this x, then this line, that's not really the slope of our tangent line, because our tangent line only touches the point at that curve. And we're really looking, if we were to zoom in on our graph and we were to take very small intervals around our A, that our tangent line would be a really nice approximation to our curve at point A, and we want to see what that slope is, or what that incline or rate of change is going to be. Okay, so we keep taking closer and closer values of x and still taking the secant lines there and trying to get closer and closer. So that suggests a limit. And we could have easily just taken values on the other side as well. So we want to define our instant rate of change, or our slope of our tangent line, to be a two-sided limit. Okay, and here's what it is. Okay, the tangent line to a curve y equal to f of x at our point A, f of a, is the line through P with the slope, the limit as x approaches A, of f of x minus a over x minus a. So to be clear, it is the limit as x approaches A of the slopes of the secant line. Connecting x f of x and a f of a. So your x is getting closer and closer to A, and we define that the limit as it approaches A is going to be the slope of our tangent line, and that's why we call it M. We, in preparation to define the derivative of a function as a function itself, we go back to our difference quotient, and we can also define our tangent line to the curve in an alternate way using the limit as h goes to 0. So it's the same exact idea. If we had our point A and we went out a distance of h, then we would have the point A plus h. This point here would be the point A plus h, f of A plus h, and this point here at A would still be A f of A. And if we were to take our slope of the secant line that connects A f of A and A plus H, f of A plus H, we would get our slope of the secant line is going to equal f of A plus H minus f of A over A plus H minus A, and that will give us simplified as H. Good? And so we can also define as H goes to 0, meaning our values are getting closer and closer to A, we will center upon the slope of that tangent line. Okay? So here we have an example of using both of them, and I would recommend using 1a, using the first definition, limit as x approaches 1 of f of x minus f of a over x minus a, when you only have to find one slope. So if you're within a particular application and you just want to find what's the slope of the tangent line at x equal to 1, then I think it's an easier definition. If, for example, you needed to find multiple outputs for what is the slope of the tangent line at x equal to 1, what's the slope of the tangent line at x equal to 2 and x equal to 3, then I would use the second definition with the a plus h. Okay, so here we go. Here's an example, f of x equal to 96x minus 16x squared. You're going to see that pop up later on in this discussion in terms of an application example. It says use definition 1 to find the slope of the tangent line at the curve at point P equal to 1, 80. So don't forget that this is a f of a. That tells me that f of 1 is equal to 80, and a here is equal to 1. Good? So we're just going to plug in, this is our f of x minus f of a over x minus a, and so we're plugging in our 1's and our f of 1's, right? Just to see where we can apply what we're given. And so we have our f of x is minus 16x squared plus 96x. We're subtracting f of 1, which is equal to 80, over x minus 1. We note that that is going to give us a 0 over 0. So we know to factor out an x minus 1. So first in this next example, we just factor out the negative 16 just to make it easier to factor the polynomial. X squared minus 6x plus 5 does factor to x minus 1 times x minus 5. And now we are able to cancel our x minus 1 with our x minus 1. And now we can take our limit, and taking our limit, we plug in the value of 1 into x, and we get negative 4, and negative 16 times negative 4 is equal to 64. If we were to use definition 2, we are finding the slope of the tangent line again. We're still using 1. We'd still understand that a here is equal to 1, and f of 1 here is equal to 80. And that's what we get with our 1, 80. And using f of 1 plus h, we need to take in our function negative 16x squared plus 96x. Wherever x appears, we plug in 1 plus h. So we have minus 16, 1 plus h quantity squared, plus 96 times 1 plus h. And then we want to subtract f of 1, and f of 1 is equal to 80. We then want to expand the 1 plus h squared. That is not 1 squared plus h squared, people. That is 1 plus h times 1 plus h, which ends up being, if you use the FOIL method, 1 plus 2h plus h squared. And then if we just distribute the 96 times 1 gives me 96, and 96 times h gives me plus 96h minus 80. Distributing the negative 16 through the polynomial, and then finally collecting or simplifying, we see that minus 16 plus 16 goes away, and we can combine minus 32h plus 96h gives me 64h, right? This minus 32 plus 96 gives me plus 64, and we still have the minus 16h squared. We then want to factor out our h, and factoring out our h, we are able to cancel h, and now we have the limit as h goes to 0 of negative 16h plus 64 is going to minus 16 times 0 plus 64, and that gives us 64. So you see the second example is a bit more complex to calculate. It's a little bit easier to calculate using the first definition of the derivative, but the first definition of the derivative is only going to give you 1. Okay, so we want to use the a plus h, and with an arbitrary we can get somewhere. And that's where we're going to go with section 2.8. All right, so that's how you find the slope of a tangent line using the limit definition. Now, how would you find the equation of the tangent line at the point 180? Don't forget that the point 180 is your point, so that would be your x1, y1. And we do have that our slope, m, is going to be equal to 64. And we want to use our point slope form, right? Don't forget that this is our point slope form for the equation of a line. And that equation of a line is y minus y1 equal to m times x minus x1. And so you do see that your y minus y1 would be f of 1, and so we would be putting in 80. And your a is equal to, or your x1 is equal to 1, and your slope is 64. And you would want to simplify by collecting all of your terms to the other side so that you are in the slope-intercept form, mx plus b. Good. All right, so that's pretty simple. So here's some applications. Velocities. So we'll be dealing with a lot of motion problems in this course, and so this is just your first introduction to those. So suppose an object moves along a straight line with a position function s equal to f of t, where s is the position, which is the directed distance from the origin at time t. In the time interval t equal to t equal to a plus h, the change in position is going to be f of a plus h minus f of a, right? So if this is at your position is up here, this would be f of a, right? Because that's our position. And then position at time t equal to a plus h would be f of a plus h. And so this distance here is going to be f of a plus h minus f of a. So you see where that difference quotient from pre-calculus is going to be very useful here. And then our difference in time is going to be a plus h minus a. Right? Our difference in average velocity is a plus h minus a, and that's what gives us a, or h, right? So, and our average velocity is going to be displacement minus time. So that would be that s of a plus h minus our s of a. That is displacement, and that is just where you are relative to the origin. It's not necessarily total distance traveled, it is average velocity, so that is our displacement over time. All right, so our instantaneous velocity would be the limit as the displacement over time as that h goes to 0 is going to be defined as our instantaneous velocity. So remember our average, so this is instantaneous velocity. Remember that our average velocity has no limit. It is the slope of the secant line, so to speak, if we had a velocity function that was not on a straight line. It would just be our f of a plus h minus our f of a over h without taking the limit. That would be our average velocity. But our instantaneous velocity would be saying, let that h go to 0, so let the values of that extra point in taking that slope of the secant line approach our original point A. Good. So again, remember we are using the same equation or same function expression 96t minus 16t squared that we used from above. A rock is launched vertically upward from the ground with a speed of 96 feet per second. Neglecting air resistance, a well-known formula from physics states that the position of the rock after t seconds is given by the function s of t equals 96t minus 16t squared. Later on in Chapter 3, when we deal with applications of the derivative, we'll return to some motion problems, and you will see even more so in Chapter 4 how we come up with these standard falling body problems. All right, it says, what is the velocity of the rock after 1 second? So this is a case where I wouldn't necessarily use the s of 1 plus h and use the limit definition. I might actually, because I only need 1, I might say limit as x approaches 1 of s of x, or s of t, minus s of 1 over t minus 1. That might be easier to do, and that's going to give me my velocity at 1. All right. It says, with what velocity does the rock strike the ground level? It's always going to be when your position function is equal to 0, right? So just think of ground level as your position wherever you are in a vertical. Position 0 is ground level. So we would first solve negative 16t squared plus 96t equal to 0. If we factor out 16t or negative 16t, we see that t is either equal to 0 or t is equal to 6. So at t equal to 0, we are at the very beginning when we're launching the rock, but 6 seconds later it will have come back down to the ground. So we want to use v of 6. And so I would, again, say use the limit because we're only saying how fast is it going at that time. You could also use the limit as t approaches 6 of s of t minus s of 6 over t minus 6. And that would be easier to calculate. Good. All right. So here, in this case, it says the position in meters of a particle moving along a straight line given by the motion equation s equals 6 over t. Find the velocity of the particle at t equal to a, 1, 2, and 3 seconds. In this case, you probably want to use the limit as h goes to 0 of a plus h, because then you will have an answer here that ends in a, and then you can just use that example for v of 1, right? Because if we have v of a equal to minus 6 over a squared meters per second, then we're going to get minus 6 over 1 squared meters per second. And you can see that it's easier to just find 1s, 2s, and 3s. Good? Because here this would be minus 6 over 2 squared, and in this case this would be minus 6 over 3 squared. And I think they made a mistake here because this would be, oh no, 9, that's right. All right, so just taking a look at that, the f of a plus h is going to be 6 over a plus h minus f of a, or s of a is going to be 6 over a, and in multiplying on the top and bottom by the denominators and then distributing, we get 6a minus 6a plus h, and in the denominator we just multiply those. We expand the numerator, and then we see that our 6a's go away, and we're just given with minus 6h, and now we can cancel our h's. And now we can take the limit as h goes to 0, and h is the only thing going to 0, a is a constant in this case, so we would be going to minus 6 over a times a plus 0, and that's going to be minus 6 over a squared, or a times a. All right, so that's when it's useful if you have to find more than one value. Okay, so the derivative. The derivative of a function, f at a number a, is going to be denoted by this notation, f prime of a. And it is going to be the slope of the tangent line at a. It's going to be the instantaneous rate of change. Did I write that right? At x equal to a. Okay. You can also, if you're only finding one, you can, the derivative of a function, this is same here. This is the slope of the tangent line at x equal to a. It is the instantaneous rate of change at x equal to a. And it is going to give you a number. Good. So we define the tangent line to the curve at the point A to be the line that passes through P and has that slope given by these two equations. Okay. So just to reinforce, your average rate of change is just your change in y over your change in x, and you are given 2 points on your curve, right? And it would be your f of x2 minus f of x1 over x2 minus x1. These are used, and we can use delta y over delta x. So your delta y is that change in y, and your delta x is the difference in your x values. And your instantaneous rate of change is the limit as the delta y over delta x. So this is another alternative expression that you would see in some calculus textbooks. It's very useful later on when we deal with differentials. Okay, and later chapter 3. Okay. So remember, just as that example, and we're going to use motion as a lot of our examples here because this is calculus for engineering students. Notice that velocity, y is the derivative of the position function, the velocity function. If s is going to be inputting, if s of t gives me a position at time t, so t gives me a time unit, right? And s of t is going to give me a distance unit. As an example, it could be seconds, right? E.g., for example, distance unit, this could be in meters, right? And if your velocity is your instant rate of change, not average velocity, but instant velocity at t equal to a, your instant rate of change, that is a limit as t approaches a of s of t minus s of a over t minus a. And s of t is going to give me meters. S of t minus s of a is going to be meters minus meters, and that's going to give me meters. And t minus a is going to be time minus time, and that's going to give me seconds. And so you can see that your velocity is going to have units of measurement as meters per second, miles per hour, meters per second, feet per second. And so you see that the derivative of the position function is going to be the velocity function. All right. Velocity can be positive, which means that the object is moving forward, If velocity is negative, it means the velocity is moving backwards. In the examples of vertical motion problems, like launching rocks from ground level, if velocity is negative, it's moving down towards the ground, and if velocity is positive, it's moving up into the sky. Okay, so that's why in the earlier examples you saw that we were moving at negative. So we'll see in other examples. But backwards, think of negative velocity as moving backwards and positive velocity as moving forwards. And the speed of your particle is the magnitude of your velocity, and so that would be the absolute value of your velocity. All right. So just other examples, we can use derivatives in all sorts of different applications. So for example, in business, here, a manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards of this fabric is C equal to F of X dollars. So in looking at that, so it says, what is the meaning of the derivative F prime of X? What are its units? So remember, your C equal to F of X inputs yards, right? And C is going to output dollars, right? So our F prime of X equal to the limit as X approaches A of F of X minus F of A over X minus A. We're going to have dollars, right, in the numerator and yards in the denominator, right? So what is the meaning of the derivative F prime of X? What are its units? It's going to give us the instant rate of change of manufacturing or producing, I guess, yeah, manufacturing bolts, A bolts of, or X bolts of fabric, right, in dollars per yard, right? So, or A bolts of fabric. So your F of X, F prime of X is going to give you a formula to calculate how many, what does it cost to manufacture A bolts of fabric in dollars per yard. So in practical terms, what does it mean to say that F prime of 1,000 equals 9? So you can say in part B, it costs $9 per yard to produce 1,000 yards of fabric. That's the going rate. So if you wanted to produce another yard of fabric, it's going to cost you $9 per yard, just at the very next one. And you'll learn later on that they defined the derivative of the cost function is the marginal cost function, and the marginal cost function is the derivative of the cost function. Good. C, which do you think is greater, F prime of 50 or F prime of 500? If it is the cost per unit, my guess would be the more expensive one would be the smaller one, right? I think it would be more expensive to produce 50 yards versus 500 yards, right? Or the rate at which, because if you have mass production, it might end up being cheaper to do more of them. So my guess is that it would be the first one. All right, that does it for section 2.7. Please join me for section 2.8 as we introduce the derivative as a function. So then we can really expand and move forward with applications of the derivative. Take care.